In this video, we're gonna to explore what are the wind tunnel results and compare this result to the Xfoil results. We're gonna to use the work of this professor, Michael Selick, Illinois University. He had done many wind tunnel tests, and the good news that the book I was buying a long time ago is now for free on internet and you can download it. And so you can learn a lot because there are dozens of profiles who have been wind tunnel tested. Because most of the time, the average wind tunnel tests for graduate students are about NACA 16, NACA 18 symmetrical airfoil, and we have no interest in this type of result as radio control hobbyists. Why it matters? Because simply we are in the domain of the low Reynolds airfoil, which means that the speed of our gliders of our aircraft are so low that we are exactly in the scope of this type of test. With this test, we also gonna to know more about the behavior when we are deploying flaps from 40 degrees to minus 40. Let's start. So we're gonna to try to answer to some question in this video. How far Xfoil results are from the wind tunnel test, and this depends on the speed, which translates in Reynolds. First question. Second question, is Xfoil capable to predict the stall? Yes or not? Or maybe it could help to guess when the stall happens. What are the value of the drag and the lift depending on the alpha, on the incidence? How far are the value from the wind tunnel result? And also, generally when you use Xfoil, when you are setting some flap, after 6, 8, 10 degrees, you start to understand that there are some problem of convergence into Xfoil and you cannot export the result. And I don't even speak about flaps 20 or 40%. And the value of this wind tunnel test is that we have a return of experience what happens at 20 or 40% minus or plus. And that's something that you cannot have in Xfoil. So we're going to study in Xfoil and in the wind tunnel two profiles. The first one is an old generation of A5G done by Mark Dweller. This is the AG40d, and this profile is the root code of the Supra that has been produced by Vladimir Models in Ukraine. 3.5 meters. So the thickness is 8% and the camber is 2%. It's an old generation, but still very useful to look at. And the second profile is also an old generation for F3 glider, root code. And this is the AG455ct with a thickness of 6.46 and a camber of less than 1.8%. I think these two profiles are quite representative, and they have been designed specifically for radio control glider by a guy who's not only a master in aerodynamics, but also an hobbyist like us. He's flying and he has flown a lot of radio control glider. We will watch this step by step. My work started in XFLF5. I opened two profiles and I set up the different flap. But before this, I smoothed each profile through Airfoil editor. So I did a previous video about this. I will give you the link in the commentary. And after I have asked Xfoil to calculate each polars, of course, I've been using the batch analyze, where you can specify multiple profile and you can set up the number of Reynolds you want here. So here we have 15,000, 45,000, and for a specific range, started from minus 4 degrees to 15. I kept the standard and create a level of turbulence 9, and I have asked to draw the polar I was interested in. So in the document, we have to go bottom, and we first have the Kepler 387, but we are not interested in this one. We are interested in this one, and you will see that the theoretical profile is compared with the sample put into the wind tunnel, and so we have some discrepancies here. And we are interested in this page with this drawing at 100,000 Reynolds. It's approximately a flight at 6 meters per second for 24 centimeter chord. It's likely to be a F5G rather than F3K, but we have no other data available. I would have liked to have a drawing at 60,000 Reynolds for F3K. It would have been more relevant, but we don't have. We need to deal with this drawing exactly. So you can see that we have this value of flap, minus 15, 0, 15, 30, and 40 degrees. We are now comparing the first curve, which is on the left in triangle, and this is the black one on the Xfoil graph. You can say that the two curves looks like the same, but if we look carefully at the end of the curve on the top left, we can see that Xfoil is over-predicting the lift. So we reach something like 1.1%, 1.1 here, or maybe 1.15. And in the wind tunnel, we reach no more than 1 of lift. And if we look carefully at the end of the curve on the top left, we can notice that Xfoil is underestimating the drag. In the reality, the profile is more draggy when we start to reach 0.85, 0.9, or 1 of lift. That's the first lesson when we are watching this profile. Things start to be really worse when we talk about profile with flap highly deployed. When we look at the profile with a 30 degree flap here with a triangle, and we compare to the yellow curve in the graph on the right, we can see that normally the yellow curve should be shifted totally on the left and should be shifted along the 0.10 axis, which means that we have an underestimating of the drag of something like 50% or 40% at least. The drag is highly underestimated. And if we look at the 40 degree, the problem is in Xfoil you have just few points here, but in the reality the wind tunnel is capable to get back more value starting from 0.5 of lift to 1.5, and this is the type of information that we cannot retrieve in Xfoil typically, and that's the value of the wind tunnel. What is interesting is that even if you are trying to pilot your plane and change the alpha, the drag will move slightly whatever the angle incidence you have. And that's the same for 60 degrees. If we come back to the flap at 15 degrees, we can guess on the wind tunnel graph that the stall is somewhere here, probably after this point, because the wind tunnel was not capable to retrieve any information. If we look the green one on the right, we could believe that the stall is somewhere here. It's more difficult in Xfoil to predict the stall. Another thing interesting is the flap with minus 15 degrees. This is here in brown in the Xfoil graph on the right. And if we look carefully, we can see that Xfoil is quite good to predict the behavior of the profile with a flap -15. The drag is still underestimated when you are starting to push the limit, which means that you start to have more incidents. But that's really interesting because you better to have some negative flap during a turn rather than to have positive flap during a turn. Let's focus on the AG40d, which is the root code of the Supra. We're gonna to try to assert if the number of Reynolds is increasing, if the prediction of Xfoil is gonna to be better with more Reynolds. That's the basic question here right now. Of course, this profile had been designed for a specific range of Reynolds, and you can see here the first polar on the right of the left graph that we have a bubble that start to appear in the wind tunnel. So at 60,000 Reynolds and at 80,000 Reynolds. But this profile had not been designed to work as this regime. First of all, because at 60,000 Reynolds, we start to have discrepancies because you can see that we have 0.02 drag here, and the threshold is crossed at 0.2 of lift, while on Xfoil it's 0.4. When we approach the lift of 1 in the Xfoil graph, we have something like 0.0. We have a drag around 0.032, while in the reality we don't probably even reach this coefficient in the wind tunnel, and the drag is probably more than 0.05, which means that it's an increase of 180%. So we can see that the lift here on the Xfoil graph on the right at 60,000 results is overpredicted, and that the drag is highly underpredicted if you look at what happens on the wind tunnel curve. If we now choose the last polar on the wind tunnel graph, the last curve on the left, which is a Reynolds of 450,000 Reynolds, which is likely to be a speed of 30 meters seconds, rarely reached in F5G. Let's try to find out the discrepancies between Xfoil and the wind tunnel. If we look at the lift and the drag at 0.5 of lift, we have a drag of 0.07, and it matches the Xfoil prediction. We don't have enough grids on the graph to determine the lastest decimal, but it looks like the same, 0.007 of drag. Let's push this, let's say at a lift of 1, so it will be easier to read. So the drag is 0.015, and now we will try to find out what is the drag here. On the Xfoil graph, we have the same value, 0.15, so that's the same. So the prediction at high Reynolds is very good. Let's come back to a more average value, which will be probably 150,000 Reynolds, which for an average F5G would be around 10 or 11 meters per second, 12 miles per hour, and you are in the speed mode on your transmitter. So the value here, it's 0.011 for a lift of 0.5 on the right in the Xfoil curve. This is the blue one, continuous, so this is this one here. So we have value here around 0.1. So the drag is underestimated, probably of 8 or 10%. If we look at a lift of 1, we have a drag of almost 0.26. Let's look in the Xfoil graph. And here we have a drag of at 1 of only 0.21. So that's roughly a difference of more than 20%. Be careful even with such type of Reynolds, 150,000. You could have already a quite huge difference because 20% is quite significant. The last graph I wanted to show you is this profile of FIG at 10 degree of flap, 100,000 Reynolds. And you can see here that there is a large curve leading to less drag. So you could think, okay, I will set up the flap, get more than one of lift. And the problem is just that to get this bucket, you need to find the right spot between 0 and 1 degree of incidence. This is the alpha degree. Unlikely that you're gonna to keep this 1 degree of incidence, considering that you need to correct your flight due to the turbulence, due to thermals. It's likely to happen only during the morning when the weather activity is very low and you are making what I call a ballistical flight. Let's come back to the comparison between Xfoil and the wind tunnel. So on the right you have the Xfoil curve in violet, and on the left you have the wind tunnel. So what is remarkable is that Xfoil is predicting very well the behavior of this profile, not only about the real trend, also here this bucket, this curve here, it's almost the same value, and all along the curve, especially from 0.5 lift to the maximum, because it's unlikely that you are working at 30 meters seconds with flap deployed at 10 degrees. It makes no real sense. If we look closely, the drag is slightly underestimated, but not so much, and everything looks good. So the conclusion is, if you are aiming the right spot for what the profile is designed, so this profile is probably designed for 90,000, 100,000 Reynolds, and you are still at enough higher level of Reynolds. In this case, Xfoil predictions are very reliable. Except that, of course, we have a top lift on Xfoil that is higher than the reality, but this is usual with Xfoil.